Hi, good day everyone. My name is Kevin Sanka and I will be demonstrating my personal project titled Optimal Coil Design for Axial-Flux DC Motors in Reconfigurable Robotics. Using the Barrett-Savart law, we are able to compute the magnetic field vectors at any point in space at some distance from a current carrying conductor. From research, we know that the z-vector will not be useful as it will only add additional stresses on the bearing, because the coils will either be pushed or pulled from the magnet. This could cause the rotor to tilt and introduce undesirable wobble into the system. However, we are interested in the x-vector as it will generate torque on the system and turn the motor. With that optimization factor in mind, we can now simulate the three unicoil designs. Firstly, we can see that the Python script I created to generate the spiral coil in the Cartesian coordinate system. We are able to adjust coil parameters like number of turns, wire diameter, and wire or track spacing. Using the power of Jupyter Notebook, we can easily see our plotted coil and coordinate data frame within the program. We are also able to export this data to a TXT file for the simulation software and a CSV file for the Fusion 360. Looking at the simulation aspect, we define a bounding box around the generated coil geometry to act as the necessary boundary conditions for the intervals. We are also able to generate the magnetic fields for the x, y, and z vectors, as well as determine the peak magnitude of these vectors. Moving on to the octagonal coil, we can see basically a similar layout with the ability to adjust the same parameters from before. However, we are able to visually see the plotted coil is the correct octagonal geometry and is able to export in the required TXT and CSV formats. Examining the magnetic field graph, we can see that there is a lot of unused coil that do not produce a magnetic field in the x direction, which would affect the efficiency of the motor. Finally, the wedge coil geometry required some additional code to draw the necessary curves on the edges, but the algorithm still needs some refinement as these curves are slightly distorted. From the magnetic field graph, we can clearly see that the wedge designs has the highest peak values and better coil usage in all vector directions. Here we can see the design and modeling process of the three coils side by side in Fusion 360. This is a time lapse of the coils being 3D printed. Now with the 3D printing complete, I can start the assembly process. I'm careful not to apply too much force when inserting the wires, otherwise I can break the wafer because of how brittle the protoplaster magnetic iron-filled PLA is. In the experimental setup, you can see me first verifying the voltage at 12 volts and then shorting the leads to verify the constant current mode is set to 3 amps. You can see the iPhone magnetometer running on the desk. The spiral coil is set up and the power supply is switched on. You can immediately see the deflection in the magnetic field vectors on the magnetometer. After a period of approximately 5 to 10 seconds, the power supply is turned off. This experiment is repeated 2 more times for the octagonal coil and the wedge coil. From the experimental data, we can easily compare the magnetic field vectors of the 3 coils. All 3 coils produce a strong z-vector highlighted in green, but the wedge coil produced the strongest x-vector highlighted by the blue line. This correlates with the findings from simulations, proving that the wedge coil is the most optimal design for axial flux DC motors and reconfigurable robotics, as they are able to produce the highest torques to turn the motor. Thank you for listening and cheers!